And I certainly won't be answering questions on Wednesday before you turn them in. So if you've got questions, totally ask me. Like, you know, what went wrong here? But after that, right before class is not good. It's not good. It's not healthy for anyone. What are you doing? So you can recoup even losses. Even losses greater than 1. So if I took off like 1 point or less, it was because it was so trivial. I just wrote the correction there, and there's nothing to do. If I took off 2 or more points, you can get back half of those points.
I'm very well. You were reading it low. You even missed it.
There's a Becky. You're so well. So make sure that what I took off is the correct amount too, please. Make sure I didn't overtake off. Or anything like that. So like I think the most you could lose was like 10 points. These were 14 points each. That accrues to 98 points total for the 7 different problems. And I think the most I took off, if you wrote anything, was 10. So you can recoup 5 of those by just turning stuff in. And usually, like if you lost 10, it was because you were like doing something that could not work, possibly. Like you used parts where parts couldn't be used, or substitution where substitution couldn't be used. That happened semi-regularly. Yeah, so again, please check out the announcement. Please talk to me if you want to talk about anything. I don't want to take any, oh yeah.
Can we email over the weekends with corrections?
Ask
about it.
You can totally, yeah, absolutely, 100%. I probably won't be checking my email till Sunday sometime, but absolutely, I'll get back to you. Okay. Sound good, everybody? Good? All right. So, we have a web work floating around. I don't really want to take a lot of time today. Does anybody have any small questions on that web? Yes, Sophie.
So when you're finding x, on number 5, I found 3 different numbers for x.
Okay, take a look at number 5.
So I don't
My
know.
goodness.
You're supposed to find 3
I
because
don't
it
know what to
intersects
do
3
with that.
times.
Oh, okay. Oh, okay. So you've got, okay. That was the fun one.
2 of them.
Yeah, I thought so,
fun
but
one.
I just don't know how to work
Yes,
it.
yes. So let's take a look. So Sophie's looking at number 5, which is absolutely the most complicated. I'm going to replicate her graphs here loosely. Cool. So for this one, you found 5 different numbers.
3.
3. Okay, that's good.
It's question 5.
That's good. Okay, thanks. I knew a 5 was in here somehow. So you're going to find this x1, this x2, and this x3 coordinate. And let's say this is f and this is g. This is one of those cases where having the pictures is essential because you're going to need to look at who's on the top and who's on the bottom in each region. So this will require multiple integrals. So for this first one here, it's going to be integral, so let's call this A1, call this A2. And I get Desmos out to look at this, because cubics are hard for folks. Maybe you like graphing, so do that. But in this first one, notice f is on top, so it's going to be f of x minus g of x there. And then I pick that up in x2 and run it to x3, where g now becomes the top. and F is the bottom. You can't just run all the way through, because what'll happen is you'll get cancellation. Like if you were to run this integral from x1 to x3, because this would be a negative area here, it would end up being misleading and canceling out. So this is, Voin was talking about absolute values, but here's a case where that absolute value needs to be dealt with inside, just in case. Does that sound good, Sophie?
Yeah, that helped, thank you.
Anything else on that homework? Pretty quick one. Shouldn't take too much longer. I think a lot of folks have done a decent amount of work on it. And there will be a new one opening up today. We're gonna have a series of short web works coming up with all these different applications. So there'll be a new web work, and I think it's titled Volumes by Disks, which I want to talk about a little bit today. So we're moving into this whole application area of the integral that's really cool, but also really challenging for folks to, you got to practice, because it takes a new mindset in a way. All right, so let me clear up here. And if you're not taking notes, I ask you to not use your laptop, please. If you are taking notes, continue on. All right, so here's the basic problem, and this is going to get kind of cool. Basic problem. I'm going to take a curve. So I've got y equals f of x from some a to some b, something like that. And I'm going to spin this thing around the x-axis. So this is called a solid of revolution, which sounds like kind of cool, right? The solids of revolution, something like that. But if I spin this around the x-axis, what's going to happen is I'm going to get a shape that kind of looks like a paper fish or something, a paper fish lantern. I don't know if there is such a thing. This is my axis of rotation here. This is the line you can't see in the back, and then the axis continues out that way. So if you couldn't see that, and then maybe if I add some like shading here, that'll kind of help with that. It looks like a peanut or an elephant's nose or something like that, right? But it's nice and symmetric. And so one of the things I found that folks have a challenge with is understanding what results from these revolutions. And this is like kind of an easy one. Sometimes we'll be taking out the center and all sorts of stuff like that. So this is our problem. How do I find this volume? And what it comes down to is we need to look at this problem from first principles. We need to look at it from the Riemann sum point of view. So what I'm going to do first off, and then we'll have a formula, and you'll never need to worry about it again. So the first thing I'm going to do is take this region, which now looks a little different. That's okay. So I'm going to take this region, y equals f of x. I'm going to cut it up into n pieces, maybe equal, maybe not equal. I'll make that last one look crazy big. So I'm going to slice the x-axis into n pieces. So this is called a partition. Just to refresh that verbiage. And then I'm going to do what we would do is if we were approximating the area, we would pick a point inside each one of these. And we would make a rectangle based on the value of the function curve at that height. So I'll pick this one here. So 2, 2, 2. And then dot, dot, dot. And then just, make some freaking rectangles that somewhere touch. I don't know why I'm refusing to get up here. But I do. Oh my God, that's so sad. That's okay. It's no sadder than the fish. There we go. Okay, so I'm going to slice that thing up into rectangles. I'm going to spin the approximation to that region. So now this region is approximated with all these rectangles. I'm gonna spin that, and what I'm gonna get out is kind of what looks like a stack of coins. Literally discs though. So this first one turns into this. The next one's a little bigger, comes like this. Next one is, you know, I don't know, whatever. Let's just kind of make what this whole thing would look like. So the next one is gonna be like that. Starting to get a little shitty here. Maybe the next one's like that. And then, I'm just gonna do a couple more. Next one's kind of bigger. Oh, now they're looking like really bad coins. There we go. And then one last one on the outer edge. Oh my God. Well, that all looks psychotic enough for a Friday, so there we go. Does it make sense what I'm talking about here? Like what the process is? Okay, awesome. So if I add up the volumes of all these disks, I'll have an approximation to this volume here. So spin the rectangles to get an approximate volume, which is equal to a stack of disks. So if we can actually figure out the volume of each of these disks and add it up, we'll have an approximation to the volume. So let's just take a little foray into disks for a second and think about their volume. That's a much better disk. Feel much better about that. Let's say I had a disk and its thickness was, oh, I don't know, delta X. Seems pretty reasonable. And its radius was just R. What's the volume of that? Yeah, what you think, Scott?
Pi r squared delta x.
Damn, you've got like a good intuitive understanding of volume. Solid, absolutely. So what Scotty did was he took the area of this circle, which is pi r squared, times the thickness of this disk. So that'll be our volume of just one of the disks. Does that sound unreasonable? Yeah? All right, cool. So, let's get this approximation out now. So let delta x of I equal the width of the ith partition. And what I mean is just like these little things here, how wide is each one of these. So put a little delta x in your picture. And it's going to change. Let's make it delta x of I here. So of the ith partition, just the ith cut. That's all I mean. And let's let x of I star equal the representative point. So whatever point I picked out of here to represent the whole interval and used to just determine the height of the rectangle, that's the representative point in the ith partition. So let's take a look. We got a little picture here, delta x. I've got this, well, this is delta x wide. Get out of the way so Alan can see. And I've got something like this, and then I've got x of I star here. And I used that to determine the height of that rectangle. How high is that rectangle? R. Yes, indeed. What is R in this case specifically?
The radius of the...
It is, absolutely. These are all good answers. I'm looking for like
F of x star.
f of x of I star, right? So it's the height of the function at that point. That's the radius. So the height of this one right here, how high is that? It's f of x of I star. This one's like x of 2 star, it looks like. So just find out how high the function is at the point That's the height of that rectangle over there that I'm gonna spin. So this is f of x sub I star. Does that sound okay? Yeah? Let me know if that doesn't. I'm happy to explain it. It's good. Like I said, we're gonna get a formula you're never gonna go back to, but if you understand this, then you don't need a formula. You can always build the formula yourself. So when I spin this thing, I'm gonna have a disk. So spin. I'm gonna get a little disk that looks like this. And here's the center. The radius, so r is equal to f of x sub I star. The thickness is delta x sub I, and we've got our formula there, thanks to Scotty. So we'll call this the ith volume, and we'll call that v sub I. So v sub I is going to equal pi times the radius squared, so that's the value of the function, squared, so again, that's just r, times the thickness of that slice. That's one of these, and I just need to add those all up. So the approximate volume is going to be V1 plus V2 plus, well, we don't quite know how many we have, but we'll go out to V sub n. And so that's going to be the sum of all these things. That's going to be pi f at the first representative point squared delta x1 plus pi f of x sub 2 star squared delta x2 plus blah, 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 all the way out to that last one, which is going to have a volume of pi f of x sub n star, bless you, squared delta x sub n. So that's our approximate volume. This board looks like it's had a rough week. This is pretty bad. Questions? Is this story making sense? And that's not to say, could you reproduce this story for me now on the spot, like present it to everybody, but is it making enough sense? That's what I need to know. I guess what I really need to know is it not making sense? That would be helpful. Lots of little stuff there. When you see things with delta x's and x sub i's and x sub n's in them, I want you to think Riemann sum. This is the definition of an integral, at least the stepping stones to the integral. So in compact form, that sum, so the volume is approximately sum, so that's a sigma, capital sigma, I equals 1 to n, pi f of x sub I star squared delta x sub I. That's just a compact way of writing that thing in the lower right-hand corner of the board. Remember, this just means add up these things, letting I run from 1 up to whatever this top number is. Nothing mystical here, just nice notation, compact notation. What do you think I want to do with n to get the true volume?
As close to 0 as possible.
So n is the number of rectangles. But
It's close to infinity.
it's close to infinity, so let it go to infinity. Yeah, we do want to, so Voign's thinking of a different way to think of this. We want to let the thickness of each rectangle go to 0. And by doing that, we need more rectangles, and that produces the same thing. So let's actually say that both ways. So let's let n go to infinity, or equivalently, how about we just say the max delta x sub I, the biggest one, let that go to 0. Make tiny rectangles, thereby requiring more. This makes more rectangles, thereby requiring thinner rectangles. And what happens is this turns into an integral if things are nice. So we put here, if the f of x is nice. And we honestly, to make it not nice, we'd need like an asymptote that blew off to infinity. Something like that, like a big hole in it, or functions that you probably have never seen in your whole life that are just so weird that it takes like a whole course to describe them. So there's some weird shit out there. I'll give you an example of one in a little bit maybe, but I don't want to throw us off too much. And I feel myself drifting away to tangential land, so I won't do that. So if f of x is nice, this limit is integral. So this sum sign turns into an integral from the starting x to the ending x. That pi, we can just pull that pi out in front. It's just a constant. And then the x sub I star just becomes an x. So this becomes f of x, quantity squared. And the delta x becomes dx. Here's your formula. This is equal to the true volume. The point of doing this is so you can see how we can use the thought process behind the Riemann sum to come up with a formula that doesn't require it at all. It requires an integral. Anytime you see an integral, this is going on under the surface somehow. So take a look at that. Let me know if that makes you have anything you need to clarify, something doesn't set right with you. That's the hard part. So, all of the problems, there are 5 problems on the new WebWork. They all need this formula. This is the only formula to use on the new WebWork, WebWork 5. Don't use anything else, because it won't be right. Yes,
And then we
Avery?
just swap f of x with whatever equation is for the, right?
Exactly. So we're going to do a bunch of examples here to get us going good. Let's take a look. So example, find the volume of the solid produced by rotating y equals, oh hell, let's just make it good and easy and say 1/2 x plus 1. And then usually you get an x range here. How about we say this, by rotating the region with bounded, the bounded region bordered by, just to say things in a slightly different way than I normally do. And then here we'll put x equals -1, x equals 2, and then we'll just say the y-axis, the x-axis as well, to make things really clear. So when I sketch this all out, which you should, I would get a sense of what you're doing first. So get Desmos out, graph it by hand, whatever you need to do. This is a line of slope 1/2, y-intercept 1. So I know first off that on the y-axis it touches 1. Right, this is y equals mx plus b form. That's what I'm thinking here. And that's how I got the slope as 1/2. Now at -1, I can just plug that in and we get -1/2. So, or excuse me, +1/2. So there's that point there. And then at 1, I've got 3/2. At 2, which is the end, I'm all the way up to 2. I just got a good old straight line like that. I have the bounding curve x equals -1, that's a vertical line. Here's x equals 2, and here's y equals 0. So this is the region we're gonna spin. Just take a moment. Can you draw it? Just take a minute. Just try. It's fun to draw these isometric drawings. This is like the funnest part for me. I always done this stuff. What does that look like when you spin it about x? looks on your guys' faces as you're like working through this. That looks great. Oh, that's great. It's like a fez, right? It's a fez. Indeed. Oh, that's a nice, that's a huge fez. That's almost wearable. How's a fez going? Oh no, oh no, oh geez, it needs a battery. Do you need some paper or anything? Okay. Is that a AAA?
Yes.
I don't think I got like a double A. So, okay. Oh, okay, I'll double check. I got all sorts of stuff in that bag. Okay, all right. So what you get out is a little circle out here, straight edges like this, and a nice round bottom like that. So this is actually, it's not just a fez. A fez is a frustrum of a cone. And what that means is you took a cone, that's actually half a cone, this is a full cone. Full cone has two parts. This is called the nape of the cone. You got some axis of rotation, but a frustrum means you've taken two planes that are perpendicular to the rotational axis and cut across. So make a slice there, make a slice there. You got ye old frustrum of a cone. A little cone knowledge never hurts, right? Cone wisdom. So let's set this up. Our volume is going to be pi integral from start to finish, so -1 to 2. And we're not going to crank this out. We're just going to set these up. On the next exam, I will just have you set these up. It's like, as opposed to doing all the calculus, which can take a long time. We take our bounding curve. You'll have enough on web work. You're going to have to do them for web work. And that's it. Whatever that is the volume. And that's not too bad, is it? That's a pretty sweet integral. You could do it with substitution. You could FOIL it out, whatever makes you happy. That's our volume integral. Let's do a couple more.
So we can just leave it like that.
Well, you can for me, if that's what the problem is at hand. For web work, they're gonna want a number. Yeah, so on all the web works, you're gonna have to crank that out, still get some good integration practice. But for right now, let's just say, yeah, just write out the integral. Gosh, there's not much more to do here, but we could do a couple more. Let's see, this one's a lot like one of the web works. So let's say we've got x minus 5 in the square root, and then x is between 6 and 9. That'll make nice things underneath the square root. And then also y equals 0. So this is my region. I'll help you sketch it because this is something that folks generally don't have you might be good at it, but a square root looks like this. It looks like a parabola on its side. X is, y is 0 when x is 5. So I've got that. And then all the way out. So that is from 6. So I'm only going from 6 out to 9. So I'm really just doing that region there. Can you please set up the volume integral? Can you actually just do the volume integral? This one's not so bad because it's rigged. I mean, it's academically rigged. Let's find the volume of that weird old thing. Now we're going to find a couple other weird values that I just decided we're going to investigate. If you get done early and you get bored, sketch the volume, sketch the solid. Oh, hey. Oh gosh, is that what it turned into? So you didn't actually look at the formula. The formula says square. Square it. So this one turns out much nicer than that one. But keep in mind that you have to square the boundary. Is that okay, Cam? Yeah, I think so.
I have an order of operations question.
Yeah.
I know squares undo roots. Can we do that yet?
Oh, I please do.
That happened-
That was
did that
why I
happen
set
in the
this
beginning?
up.
Okay.
That's why I got this nasty
That
ass
felt
thing.
like deceptively nice.
It was meant to like turn into poof.
Okay.
Beautiful. Is that what you're worried about? Or no? You're not worried.
Oh, of course not. Alex says it's smaller than 5.
Oh gosh. So your volume integral should look like this. The range of your slices. Think about these slices. They're ranging from 6 to 9. That's going to become more important as we progress with this. This is the simplest thing we're going to do. That's your volume integral. Just keep on cranking that out. I would absolutely do as Sophie trepidly proposed that, and then everything's all happy. So wait. Minus 36. I wonder what that is. Is that 45? Yeah. That's 30 halves. So make sure you're getting 15 halves pi units cubed. 15.
Mm-hmm.
Yes? No? Did I do something wrong? Maybe.
Maybe.
I mean, it is quite possible.
No, I think I did something wrong.
Yeah, we're
Yeah? Anybody else getting that? Yeah? Okay, we get some other nods.
Probably.
Let's come check out. Let's see what's up. So.
My numbers just got gross. Like I really close to that, but like then they went south.
Oh wow, they really did.
I don't know what happened because that's.
How'd you get
right,
that
that's
12? I think you changed that 2 to a 12.
Oh, I
or
totally
something.
did. That's so
I think
true.
that's your
So
problem,
true.
friend.
See, like I knew what I was doing.
You're
Just-
demanding
like-
things be complicated.
Yeah,
Like this is too simple.
I guess so.
I've gotta complicate this. Any questions at all on that? I think Sophie got hers answered. Good on this? Let's just toss in one more. It's kind of actually, screw it. Let's call that. If you're not done with your web work, let's hang out here and work on that. The first web work. Whatever that one, I don't even remember what that one's about. Areas. Yeah, so if you're not done with the areas, let's get on that. If you actually want to start this one, we can do that. Let's hang out. We've got 15 more minutes together. And if you just want to leave, get the fuck out. I don't mean that in a hostile way at all. It's Friday. I'm running a scholarship activity for math scholarship takers later today. In 1 year, and I was reported by a parent for using the F-bomb. And I'm like, it's gonna be a rough 4 years for you. If this is the most upsetting thing you've seen, heard. So I have to watch my mouth now with the new students.
I think, what does the problem say? I think I just look at where those are intersect, so like this x equals 1.
And where one is.
Yeah,
Okay.
exactly, yeah,
I have a question.
yeah. Oh, you're good, thanks.
So, I know you have to do, I have my two integrals here and here.
Yeah.
Sorry, it's really small.
Well, my eyes are really bad, so.
Mine too.
Great
Look.
combo.
Yeah. So I have it from 0 to root 15 here,
Okay.
and then I have it from root 15 to negative root 15.
Okay. Well, so something is wrong here because negative root 15 shouldn't be to the right.
I know. Okay, so is that?
Let's take a look at
is
that work.
Is that negative root 15?
I don't
Well, that
know,
should
let's
be.
actually, no, it shouldn't
it
be.
does mess
Yeah,
up.
let's,
I don't know. It is so.
how did you solve for them? Right here?
Mm-hmm.
Okay. So this doesn't actually have, there's something wrong because that actually has
That'd be a negative
imaginary.
15.
Yeah, that
That's
would be
probably true.
imaginary. Yeah, so let's take a look at
I
what we got.
definitely probably didn't carry negative correctly.
Let's see, so you brought, how did you get to 4x cubed on the left?
Whoa, how did I?
Yeah.
That should be negative 2.
Mhm.
Oh,
I think
okay.
you were chilling with Floyd at Pompeii
Yeah.
there, your brain was.
Whoa.
All right, there we go. And then let's double check everything.
Yeah.
So what about x squared?
Negative 22. What the
Mhm.
hell did I do?
Oh my goodness.
I was doing
And you
something
kept on
that I
cranking,
don't
you went
realize.
cruising too.
I was. Man.
Did so much work based upon these
Yeah.
lies you told yourself.
I know.
And then let's just check everything. So,
And then that would be minus. That one is correct. That one should be 0.
is it?
Is it?
Is it?
30. No, it's 60.
Wowza.
Okay, that's where the 60 came from.
Yeah.
That part.
I think you're gonna find this is a lot better.
I think so.
Um,
So that was plus 60.
yes, man.
Wow. Okay.
So right away, 60x.
X.
That's good.
X? Oh, that's X.
So that was squared.
X.
That's x.
Yep.
I think you're good now.
Okay. And then that's all obsolete now. Great.
Yes.
Thank you.
Got
Well,
it.
actually, not entirely.
Yes.
No, not entirely. I just
Okay,
have to,
okay.
I just have to
Yes,
replace those
yes.
numbers, right? Like these
True.
ones?
Yes.
Because those, that's whoa.
And assuming that, and actually you did the simplifications correct. Look at how you did it right
I
here.
just did that. I was doing this earlier.
That was
so I don't
okay.
really know what happened.
So yeah, you're in a much better state
Okay.
of mind right now. So yeah, you're right. Just change the
Okay.
limits and like
That's nice. I thought I'd
find
have to
them
read
and
the
then
whole
change
thing.
them. No.
Okay.
Oh, you're great. Thank you. Let's talk. Okay, so which problem is that?
Number 3.
Number 3. Just really quick, when you get to number 3, you're going to have a bounding curve that is something like this, like 1 plus e to a power. And so your integral will involve that squared. And here's what I don't want you to do. The wrong thing. And here's what people will do. They'll take that squared plus that squared. That ain't true. So what I would do, Jade, is FOIL it out. So like this one here, so first, then outer, then inner, and then the last, that times that is e to the 10x. You add the exponents. And then group these together, and then you have something that's actually like you can do, right? And then don't forget, one of our best friends for the entire semester is that formula right there. Cool. Yes, sir. Oh, sorry, I'll get you a new one. I actually ripped yours off to use. Sorry. Let me get you one, boy. Let me see, let me tear it off somebody else's. Just keep moving. passing it down the line, borrowing from Peter.
Thank you. You're welcome.
Well, I bet this is yours, Moyne. But I wrote the solution to the exam on the back. That's it. Anybody here use Discord regularly? Yeah. You ever been on a server where they had Duck Hunt? It's a stupid, horrible. It's like I hate it. I don't know. It's like this, I'm trying to win a raffle ticket. Like, it's just idiotic. It's requiring I'm glad you're not doing that. Don't do it.